Here are the notes for lesson 4-6, and now we get to talk about congruence in right triangles. So remember how I said that there's no such thing as ASS in geometry? Well, guess what? We have the exception, and it is called the HL theorem, or as other people like to call it, the RASS or RAS theorem. I'm sorry to be on the borderline of indelicacy here, but here's what we mean. As long as this angle that we're talking about is a right angle, then you can use HL or RASS to prove that triangles are congruent. So here's why. First, let's fill in this theorem here. The hypotenuse leg theorem. You remember all the names of the triangle parts for right triangles? Good. Okay, so let's continue. If the hypotenuse and a leg of one right triangle are congruent to the hypotenuse and leg of another right triangle, then the triangles are congruent. And the hypotenuse of a right triangle is, you can think of it as two ways. Longest side, or you can also think of it as the side opposite to the right angle. Also, the legs of the right triangle are the two shorter sides. And, or you can say that the legs are not opposite the right angle. So filling in this diagram, we need hypotenuse for this side and legs for these two sides. Here's an example of using the HL theorem. One student wrote, triangle CPA is congruent to triangle MPA by the HL theorem. Wait a minute, what was that? Triangle CPA is congruent to triangle MPA by HL. Okay, well, is she correct? Is the student correct? I guess we don't know if it's a guy or girl. Now, that was kind of interesting, the way we ordered our letters here. C would correspond to M, so that's where I started, C and M. P was the right angle for both of them, and then A was this upper angle for both of them. So I think we named them in the right order. Now let's see if this is true. First, they're starting you off with CA congruent to something. CA congruent to, let's see, CA congruent to what other side? Yep, MA. Then we've got angle CPA congruent to angle, yes, MPA. Oops, angle MPA. And then lastly, what is PA congruent to? Haha, PA is congruent to itself. What was that property again? Yeah, reflexive property. So we have just shown that we have a hypotenuse congruent to a hypotenuse. We have a leg congruent to a leg, and we've got a right angle. So if I go in that order, pointing to the angle, then the side, I'm okay. This is the only time, only in right angles, can we do the ASS theorem, but we try to be a little more proper and call it either HL or RAS. I'd much prefer HL myself. Okay, so since AC is the hypotenuse and PA is a leg, and it's shared by both of them. MA is the hypotenuse on the other side, and PA is another leg of the right triangle. The triangles are congruent by And you can just use the abbreviation HL, or you can call it HL theorem. The student is correct. Next page. We're going to use the HL theorem to decide on some more congruent triangles. It looks pretty similar, doesn't it? Well, here we go. This is the flow proof, so a flow chart. And we have to write a statement and the reasons here. So why can we say that xm is perpendicular to yz? Well, look at this. From the vertex, a perpendicular is drawn to yz. So x perpendicular drawn down perpendicular to yz. Oh, because they told us so. And then why can we say that xy is congruent to something else? xy. Well, first of all, what is it congruent to? Hey, I get tick marks. That tells me that they need xz in the box. And where is that? They're telling us x, y, and z. X, y, z is isosceles. That means we are using the definition of isosceles. Sorry. Isosceles. We're using the definition of isosceles, where two sides are congruent. Then, what else can we say? Well, xmy, this guy, and xmz are right angles. And we can say that they're right angles because we just said over here that there were two perpendicular lines. Definition of perpendicular says that it creates right angles. Then we also have xmy and xmz would actually be right triangles because they have right angles. So now, what else do we need? We've got a right triangle and a right triangle. We've got a side congruent to a side. We also have xm congruent to itself. What property is that? Yep, reflexive. So now, with all of this stuff, I can say that the two triangles are congruent because I've proved something about the hypotenuse, the leg, and it's a right triangle. So I get to use the HL theorem. Two-column proof. Great, another HL theorem proof. My favorite kind, of course, is the two-column. So ABC, first let's read the givens. Angle ABC and angle DCB. So ABC, let's try that again. ABC and DCB are right angles. Great. And we know that AC is congruent to DB. AC, so this line here, is congruent to DB. Oops. So I'll color code those a little bit. Now we have to prove that the two triangles are congruent. All right, well, ABC and DCB are right angles. And that's given. This triangle and the other triangle are right triangles. Well, we did ABC for the first name. Now let's do this upper one. Let's go DCB to name that. And why can we say that? Well, kind of a unsatisfying thing, but we say it's just the definition of right triangles. Right triangles. Now, what else do we need to say? AC is congruent to the other hypotenuse, DB. And why do we say that? Because they told us at the beginning. So we say given. Number 4, we don't know what to write, but the reason is reflexive property. Yay, jackpot. So what could we mean here? What statement do we need to make? Yeah. BC congruent to CB. So then we've proven the leg, we've proven the hypotenuses, and we have right angles. So these two are congruent, DCB, because of the HL. Last page. Which two triangles are congruent by HL? Well, we need hypotenuse and leg. Well, this one, there's the hypotenuse, there's the hypotenuse, there's the hypotenuse. The last one, I don't know anything about the hypotenuse, so I can't use it if I'm trying to prove that other stuff is congruent. Of course, we needed right angles. We had those in all three. And of course, we need a leg, which would have been this side, or this side, or this side. But in this case, we get these two that are congruent. So let's write a congruence statement. Triangle LMN is congruent to, how are you going to name this triangle so that we've got the corresponding parts here? Show me your answer. Triangle what? Now we have to write a paragraph proof. Well, you know what? We're going to go 2 column. So here are our statements. Here are the reasons. So first, since we have example 2, which is on page, the previous page, 86, we needed to sort of rewrite their flow proof as a paragraph proof, but I want you to rewrite it as a 2-column proof. So we usually start with givens, and that's exactly where we're going to start here. So if you have these 2 pages, you can refer to the other side. I can't flip back and forth quite so easily. So here we go. First, I'll write one of the givens. XM is perpendicular to YZ. Oops, and let me number these statements. That's a 1. Here's an A. 1, 1, 1. And let's see, they also told us that we have an isosceles triangle, so that means I can say YZ is congruent to, oops, sorry, I wrote that wrong. XZ is congruent to XY, and those were the 2 legs, 2 sides of the isosceles triangle. So in the given, in the statement that they gave you at the beginning of example 2, they said, you have an isosceles triangle. So we didn't say here, this is an isosceles triangle. We took some information about isosceles and gave a congruent statement. So we're actually using the definition of isosceles. It's not a given. If I had said, I got a triangle that's isosceles, then I would have written given. Since they gave us that information, and then we're using the next step, the next logical step of information about it. That's why I'm writing definition of isosceles. So far, we've got a perpendicular line, and we got 2 congruent sides. Now, what else did they give us? They told us that this line here was perpendicular to this line. So, but I'm not going to write that. I'm not going to say this is perpendicular to that. I'm going to list the angles as right angles, and that would be the definition of perpendicular. So this will be X, M, Y, and angle X and Z are right angles. So definition of perpendicular. So I got a right angle, I got some hypotenuses, and I also have to state that these actually are right triangles because HL only works if I have right triangles. So I'm going to make sure and mention that. Hey, these are the correct type of triangle to work with. R stands for right, triangle there. And what's the last thing I need? I don't know anything about these sides down here, but I do know something about this side, which will be called a leg for each of these triangles, and that would be that XM is congruent to itself. That would be a reflexive property. So now, because I have right angles with hypotenuse that are hypoteni that are congruent and legs that are congruent, now I have congruent triangles. X, M, Y, congruent to X. Whoops. I'm sorry. I screwed up something here on number 4. We needed to say X, M, Y, and X, M, Z. So this guy should be Z. There we go. X, M, Z. So here are my 2 triangles. X, M, Y congruent to X, M, Z. And that is simply hypotenuse leg theorem. And the last question, number 3. So, you know that 2 legs of one right triangle are congruent to 2 legs of another. Explain how to prove the triangles are congruent. So here's what they're saying. I have a right angle here, and I have another right angle here. We'll call it ABC, XYZ. And they're saying we know that the 2 legs are congruent. Well, here's this guy and this guy, congruent to this guy and this guy. If this is all you know, can you prove these are congruent? Yeah, you can. You didn't have to use HL. You have side, angle, side. Whoa, what was that? Side, angle, side. So just because we're using right triangles doesn't mean we are limited to only using the HL theorem. It's still an angle, and if it's congruent to another angle somewhere else, sometimes we can just go back to our regular SAS kinds of things. In some textbooks, they do call this simply the LL theorem, leg, which works, but it's really just a reiteration of SAS. So there you go.